Hi everyone, we are the Polaris chassis team and we'll be talking about what we did over the past semester. So just to go through who we are, I'm Robert Piston.
I'm Oscar Frias.
I'm John Howland.
I'm Nick Saccone.
Bernhard Walker.
Kevin Armendariz.
So the whole motivation for the project was that Astrobotics was commissioned by NASA to carry a scientific drill and oven to search for water at the south pole of the moon. So with this in mind, we jumped into building the chassis for the Polaris. What we accomplished during this semester, as Red would say, spilling the beans, we fabricated 5 swing arms, as you can see here in the front. We tested 1 to failure, and the other 4 are ready to be machined and attached to the chassis. And we also fabricated the center beam that you can also see here for the chassis. And as you can see, the Polaris is going to be very big. So yeah, it's going to be huge. So let us explain how our process was. The first thing that we needed to do was to characterize our material, as most of us were new to working with composites, and mainly all the parts are built with carbon fiber. We needed to understand how our process would affect the properties of the material. Why? Because the data that is provided by the manufacturer really doesn't reflect any of the variances that inexperienced team as us can introduce to the fabrication procedures. And so in order to understand how these parts would behave, we really need to understand all the properties. We followed the ASTM D3039 standard for uniaxial tension. I want to let Kevin now talk about the results.
Yeah, just like Oscar said, we had to characterize the material through the use of the Instron testing machine. These are all tension tests. We tested different strand orientations that we were going to use. Here's the example of one of our tests. It matches a typical Instron test for a composite. Composites are very brittle, so they break very rapidly. They just snap. There's no ductile region at all. That's why it comes up and then just drops off. On the right, there's a table which tabulates all of our findings. The quasi isotropic test, which is at the bottom, that one failed because as some of the samples that are passed around, they're only about a ½ inch wide. And in order to do the proper quasi test, you need a complete strand at a 30-degree angle from one end of the clamp to the other, which would be probably about that long. And since we only have small little segments of fibers that fix together, it failed because there's not enough fiber running across to actually take any load, so it's not even quasi. But the other tests, most of them were very successful, and then there was a few little mishaps just from the tab slipping off and off axis from just user error. But with that.
To create our different pieces, we designed and then fabricated 2 sets of mold, once for each of the 2 types. We explored several different designs for our fabrication and settled on this one. We have 2 high temperature fiber foam pieces, which are then sandwiched around a metal insert, which we can remove to allow the entire mold to be removed easily once we finish the carbon fiber. And all of the pieces are held in place by 2 pins. This is the sidearm piece, and we have a functionally similar design for the side mold and center mold pieces, only just on a much grander scale. We fabricated all of our foam pieces on the large DFAB CNC machine, which gives us our initial rough cut for our designs. Once that's fabricated, we begin the process of sanding and then epoxying and then resanding with progressively finer grains of sandpaper to get the smoothest possible surface to be able to get proper releasing for each of our molds. Here we can see each of the 2 sets of completed Polaris mold pieces for the side arms. And here's the final jumbo size side beam piece, which allowed us to create this.
So the first step in engineering a composite part would be a computer simulation, and we used a finite element package known as ANSYS. Basically what ANSYS is it's a numerical simulation software. ANSYS is very broad. They can do structures, fluid dynamics, electromagnetics, and we obviously use the structure simulation. So the way it works is it breaks down an individual part into very small segments, and it's been proven that as these small elements get smaller and smaller, you achieve what the real solution is. So we break it down into really small elements, and we run this numerical simulation. The next step would be to apply the loading conditions, and the far end is fixed, and we applied 2 bearing loads and a side skid load to where the wheel would be, and the wheel would be located at the end closer to me. The failure criterion that we wanted to look at was known as SIWU. It's very popular for anisotropic composite materials. The equation is listed, and we want this value to be less than 1. And so there it is. And so when we looked at the SIWU failure criterion in the ANSYS model, it told us that all of the values would be less than 1, which was a good thing. And obviously the point of failure would be towards the shoulder side due to the moment. So the moment due to the skid steer load was our critical load that we wanted to further analyze and test to validate our results. And then the ANSYS for the chassis this is what it would look like. We took the case where it is actually stuck and skid steer on a rock, similar to what the wheel team analyzed in their a presentation. You can see there's a load due to the bucket wheel. We assumed that the bucket wheel actually hit a really large rock, and in the data that was presented in their design review, it was about 120 newtons, and then we added a factor of safety to that. And then the remote load that you see at the end is the hopper, is a full hopper plus a dynamic factor and a safety factor.
All right. From the ANSYS, we actually ran several iterations of the ANSYS to figure out which combinations of layers would give us the best rigidity for the applied loads. The solution we came up with was a 5-layer approach for all of the pieces. And since it's really important that the layers are symmetric, so this means what we used is a 30, plus 30, minus 30, and 0 degree, and then you go minus 30 and 30 again. That way you have a symmetric layer, and when the carbon fiber cools after you bake it in the oven, each side has the same stress, so the carbon fiber doesn't warp. We actually, when we fabricated our first strips, didn't take that into account, and we had potato chips as a result. We had the 5 layers for these, so these stay perfectly straight. Here you can see how we actually laid them up. The top right picture, you can see the first layer being put on. It's one of the 30-degree layers. The next one would be opposed to that. Then you put on a 0-degree layer. Then you put the opposed layer, and the last one that goes on is again in this direction. This is us actually applying the resin, applying it to the mold, packaging it, and putting it in the oven, and then unwrapping it. And it's really like Christmas. You unpack it, and it just looks great. Whoops. Yeah. Why does it? No. What the hell? All right.
There it is.
Okay, and this is the same thing what we did for the small molds. This is for the larger mold. What we found is as the part grows, even though we can use larger strips to wrap around, you can see the strips on the bottom, those diagonal strips, they're about almost 3 times as wide as the ones we use for the small parts. but it gets increasingly hard to line them up right, because the important part isn't so much that they meet at the ends perfectly. It's more important that we actually have the right angles, because that's what's going to be taking the load later on, since carbon fiber is only strong along the fiber. So we had to make sure we actually get the angles right, and with the larger parts it gets really hard because the gravity actually pulls these things down and slowly starts sagging on all sides, and it was difficult. But we finally succeeded. We wrapped it, and that's the result for that. So we have the four swing arms that are done, and the fifth one that we tested to failure. They're weighing at 0.7 kilos each, and we have a mass target of 0.65 kilos. But these are actually all longer and heavier than they need to be because they still need to be machined. So once we machine them all, we're aiming to be under our weight target. The center beam actually was a big surprise. We calculated it would be much closer to the 2 kilogram load. It weighs at 1.6 kilos and a few small ones, and it's not even machined yet. There's going to be 4 inches cut off of this, so we're going to be way under our mass.
Okay, so we made the parts. Now we need to see if they actually work. So our first attempt at testing the swing arms was to place 2 wooden blocks on each end just to prevent the swing arm from collapsing on itself, and drill a hole through the center and put a big 1-inch pipe through it and hang a weight from the end. So we hung the weight and it touched the floor. So that failed. We need a different approach. So the second test was to sandwich this thing between 2 steel plates, which you can see on the picture on the right, and then clamp that to a forklift, and then gradually raise the swing arm while we have load being applied at the end. And our load was, we varied it between 500 and ultimately 600 pounds. And it ultimately broke at 606 pounds, which was much more than the static load requirement, which was 120 pounds approximately. So we have a video which demonstrates the testing in action. Yeah, do full screen.
That's not full screen.
No, that's the other one. It's that. Yeah. So the first test was 500 pounds, and we just raise it up as slowly as possible so that it's as close to a static load as we can achieve. So it held 500 pounds with relative ease. Yeah. So now we're going to skip ahead to the failure case. I think it's a little farther. Yeah. So this was the loading case under which it failed. So just in case you're wondering, the 2 big plates down there are steel. Each weighs about 250 pounds. And then to get the extra 100 pounds, we had just regular weights from a weight room lying around. So we start to raise it up. You can sort of see the beam bend slightly, and it comes off the ground. And we heard a little bit of cracking, so we decided to let it sit. And then eventually you're going to see it just sort of snap down. That's eventually, yeah. So that's how it failed. The failure mode was in compression, which is to be expected, and it was right at the point where our wooden block ended inside, so it wasn't supported. But this was considered a successful test. Down. Yeah. Okay, so over the course of the semester, we also encountered some obstacles. The first was JB weld failure during the Instron tests. You For those of you who got the test strips, you could see some of the tabs on the end have come off. Another obstacle was the robot arm in Will Simon High Bay broke, so we weren't able to use that to fabricate our molds. Also, the mold release on our first swing arm that we made failed, and we destroyed that mold, so we had to refabricate it again. Our molds were shrinking, but just barely. And lastly, the first test setup didn't work as I described. So for future work, we need to machine the current parts we have to their final shape. We're going to need more carbon fiber to actually make the side beams of the chassis. We need new foam so that the molds don't shrink, and we need to fabricate the 2 side beams.
So finally, we'd like to thank a few people who really helped us throughout the semester and made our project possible. First and foremost, we'd like to thank Wenny, who was just always there for us. I think every single group in this room can just extend like great thank you to Wenny. We'd also like to thank John Thornton for all of his advice and just taking us under his wing and teaching us everything he knows. Same thing with Steve. Steve also helped us throughout the entire process. ANSYS, you name it, he's always around and willing to help. And finally, we'd like to thank Chuck Whitaker for helping us out with the test, testing the swing arm. And finally, my friend who saved us, my Archie friend who saved us, Kevin, and he's a DFAB lab monitor and volunteered his time to help us with RhinoCam. They don't use MasterCam, they use a different machining program, and really taking a lot of time out of his busy Archie schedule. If you don't know anything, Archies they just don't sleep. They're pretty amazing, and he helped me out, machined 2 sets of swing arm molds, and then the large side beam mold. It's over in the composites room. It's really too heavy to bring here, so if you want to see that, it's over there. Yeah, it's also still a little warm from the oven, but yeah. And then that's our acknowledgments. So, does anyone have any questions?
You pass around the big side beam piece, and where the metal was in between the 2 foam blocks, you can see on the part like a little bump or like a divot almost.
Yeah,
Do you think that will be a cause for failure?
no, because that's at the end, and that part's longer than it needs to be, so we can just cut that section off.
Yeah, we're also gonna fix that for the next time.
So, based on your analysis and your completed pieces, do you have an estimate for the entire chassis mass, and is it what was expected?
So, the side beam parts, when we went back and looked at the mass budget, they were 2.5 kilograms for a side beam, and so we thought that that mass needed to be increased. But we shaved mass off on the center beam, and we were hoping to use a little bit of the mass allocation for the wheel, but we definitely think that in the end we'll be under the mass allocation for the carbon fiber parts.
To give you an idea real quick, the center beam that went around is 36 inches right now.
Double that for the side beam.
The side beams are double that length, yeah. So,
Why do you think the center beam weighed so much less than you expected?
Well, the way we took a rough estimate was we used ANSYS to, it gives you a surface area approximation, and it's approximation. In addition to we took the supplier's density properties, so it really doesn't tell you. There's a lot of factors that go into your weight, and one of them is the amount of resin that's in your part. So if you get a very high, very high
Fiber to resin.
Yeah, very high fiber to resin ratio, or just a very low amount of resin in the part, because you want, there's like a really perfect amount of resin that you want in your part, and you can achieve a very good weight and performance from the part.
You mentioned that the release failed in the first test and attributed that, at least in the words, to mold release. Was it mold release, or was it method, technique, something wrong in the design?
It was part of the method. We weren't sealing the mold before applying the mold release, so the mold was still porous, and the mold release wasn't able to release it.
Yeah, John thought that applying mold release should work, but he also had his doubts about the mold release, he told us, just because it was old. But then, as soon as we found that out, we were like, okay, well, let's seal the mold first, just to get rid of all the micro porosity that could possibly be there from the epoxy. And as soon as we did that, it slid right out like butter. So.
Did you have that aluminum insert in your first mold that you had to break, or was that a later development?
No, the aluminum insert was not broken. We made another one that was a little longer, just so it would be easier for us to hammer it out if it was necessary. But what ended up happening was it just slid out. Yeah, the mold sealant worked very well.
To answer your question, yeah, the aluminum was always present since the first mold design. We've always thought about this third metal insert to be able to collapse the mold and retire it from the part. Any other question?
On the big section, the surfaces are large, so everything flexes appreciably and easily. Are there second order mechanical effects not captured in the linear ANSYS analysis?
Well, so in the ANSYS analysis, there are two other parts. There would be an end cap here, and then another part right at this end for the wheel to connect to. And what actually ends up happening is you can see that, like, I can squeeze this and it deforms a little bit, but as soon as those end caps are in, and this is in the ANSYS analysis too, we define the materials as aluminum. Those metals in compression give this even more strength
You can show
than what.
the test.
Would someone button up the ANSYS analysis that was also pointed to? This is changing to the topic of the stress and failure condition. So
Yeah, what you can see here is we simulated those end caps with wood blocks here for test, and it gives the part a lot of rigidity that by itself it doesn't have.
And keep in mind, that's already a failed
the one
part.
that's colorized and shows one hot point. There you go. So this is just a clarification of the load condition, because when this was described, what was said was the skid steer loading.
Yeah.
So does that mean that what we're looking at is a bending, or is it bending on two axes? What is it that causes the hot spot?
Okay. What causes this hot spot is actually, so there are two loads. There's a torsional load and a bending load. And so if it was just a bending load, you would see a hot spot along the line, and that's where we expected it to break. But the hot spot is now up at the corner because it's also applying a torsional load. But when we went through the numbers, we realized that the torsional load wasn't as significant as the bending load, and the bending load would be what caused failure in the end. So that's why when we tested it, we just wanted to test the bending load.
Thank you.